The speed of light that we've already talked about before is about 3.00 times 10 to the 8th meters per second. While on a 20-degree day, the speed of sound is about 343 meters per second. Now, let's imagine that a lightning strike occurs some ways away, let's say 1 mile. 1 mile, about 1,609 meters. Now, let's figure out how long it takes for the light to get to us and how long it takes for the sound to get to us. Well, for the light to travel 1,609 meters at 3 times 10 to the 8th meters, it takes 5.36 times 10 to the minus 6 seconds. About 5 microseconds, 5 millionths of a second. Very, very fast, basically almost instantaneous. Now, what about sound? Well, sound, 1,609 meters divided by 343 meters per second, is 4.69 seconds. It takes more than 4.5 seconds, let's say 5 seconds, longer for the sound to get to us. So when lightning strikes, we see the lightning almost immediately. But it takes almost 5 seconds for that sound, the thunder, to get to us. So, the old idea is, if you see lightning, see a flash of lightning, and then count 1, 2, 3, 4, 5. You count up the number of seconds before you hear the thunder, you divide by 5, and for every 5 seconds, that will be about a mile off. If you divide by 3, that will tell you how many kilometers away it was. So, that's kind of an interesting way that you could determine how far off a lightning strike was by counting the time between the time you see the lightning until you hear the thunder. Okay. Now, another phenomenon of waves I'd like to talk about for a second is something you might have noticed. If you've ever stood on the sidewalk and heard a car go by, what does it sound like? Well, I think it sounds kind of something like this. This is called the EU effect, although some people call it the Doppler effect. Now, this is something that happens with waves when either the source of the wave or the listener or the observer of the wave moves relative to the source. So if the source moves relative to the observer, or if the observer moves relative to the source, or both, there is this perceived change in the frequency or wavelength of the wave. So how does that happen? What's going on? Well, let's imagine we have a wave that is being created by a source that's stationary. You can think of this very much like dropping a pebble in some water. It creates waves that propagate out circularly symmetrically from the source. And let me put up a little diagram of what this would look like. So here's a wave where the source is right in the center and it's sending out waves in all directions circularly symmetrically. Now, what if the source were actually moving to the right? What would it look like in that case? Here we have the source moving to the right. Now, notice over on this side, the wavelengths are crunched together. They're smaller, while on this side, the wavelengths are further apart. If someone were standing over here, they would perceive a shorter wavelength, in other words, higher frequency. Someone over here would perceive a longer wavelength, in other words, lower frequency. Now, if this were actually passing by someone, as this moved to the right, they would hear a higher frequency, and then as it passed by, they would hear a drop in frequency and then perceive a lower frequency. So they'd hear a change in the frequency as the object went by. And that's what we call the Doppler effect. Now, what if the source actually were to move at the speed of sound? Now we notice the waves piling up on top of each other over here. We get a very, very strong wave front where the waves have piled up. And what if the source can actually move faster than the speed of the wave? We get a situation that looks like this, where the source has actually left the waves over here, and we end up with waves piling up on top of each other along this edge and piling up on top of each other along this edge. Now, if you're, say, standing right here, you don't hear anything because the waves haven't reached you yet. But as the source passes by, and you get hit by that wavefront, and it really is kind of like getting hit, you hear this like, it sounds like an explosion. And we call that a sonic boom. Because those waves have piled up, it doesn't sound like a sound wave anymore, it sounds like an explosion. That's what happens when something travels faster than sound. It builds up this wavefront in front of it that then sounds like a sonic boom. So how can we calculate how this wavelength changes due to a motion of the source and or a motion of the observer? Well, I'll just give you a little idea of how we go about doing it, and then I'll just give you the final result. Let's imagine we're just considering a movement of the source. So let's say here's the source, and it's giving off waves of, let's say, wavelength lambda according to the source. So it gives off a wave, and let's say that this wave has just been received by an observer over here. Well, the source is moving, let's say the source is moving at some speed v sub s, the source velocity. Now, the source will give off its next wave. Let's say that it's just given off the next wave when the receiver has just gotten this one here. So this one has just left this point. But the source is still moving this way. The source will not give off another wavefront for one period, let's say t. But in that time, the source will have moved a distance closer to the observer, let's say of Vs times t, at which point it gives off its next wave. Well, the perceived wavelength that the observer will have is a shortened wavelength, which will be the original wavelength minus this distance that the source has moved. In other words, Vs times t. Now we know t is 1 over the wavelength, 1 over the frequency, and the frequency is the speed divided by the wavelength. So we can actually determine a relationship between the perceived wavelength and the emitted wavelength using the speed of the source and the period of the source wave. And we can put that all together. Well, then we can figure out how do we take into account a motion of the observer. Well, I'll just give you the final result. The relationship we're going to use is that FO equals Fs times the quantity V minus VO divided by V plus Vs. Now, let's be very careful and make sure we define all of these quantities. Vs is the source frequency, so the frequency that the source believes it is emitting. VO is then the observed frequency. This is not like F naught where this is the original frequency. Be careful, this is FO, the observed frequency. What does the observer receive? V is the speed of sound, Vs is the speed of the source, and VO is the speed of the observer. Now, I want us to be very, very careful because there is a particular sign convention I want us to use for Vs and VO. And that is, they are positive if the motion is away from the other thing. In other words, if the source is moving away from the observer, so let's say we have a source here and an observer here. If the source is moving away from the observer, then Vs is positive. If the source is moving toward the observer, Vs is negative. So negative if toward. And likewise for the observer. If the observer is moving away from the source, that's positive. If the observer is moving toward the source, VO will be negative. So, away is positive, toward is negative. Just think of it in terms of, is the velocity tending to increase the distance, in which case the velocity is positive? Is the velocity tending to decrease the distance, in which case the velocity is negative? For both Vs and VO. So let's stick some numbers in here and make sure we understand it. So here's the problem. Let's imagine we have a source of sound with a frequency of 500 hertz. We have an observer over here that's listening to the sound. Now the source is moving this way at 35 meters per second, while the observer is moving this way at 25 meters per second. Let's say the speed of sound is 343 meters per second. What is the frequency that the observer hears? In other words, what is FO? Well, let's figure that out. FO equals Fs, the source frequency. The source frequency is 500 hertz. Times V, the speed of sound, 343 meters per second. Minus VO. What is VO? VO is the observer speed. Notice the observer is moving toward the source, so that VO is negative 25 meters per second. So we subtract negative 25 meters per second. Divided by V, again, 343 meters per second, plus Vs. Now what is Vs? Notice the source is moving toward the observer. So again, Vs will be negative 35 meters per second in this case. Negative 35 meters per second. Now, notice we have minus and negative. We can make those plus. We have plus a negative. We subtract that. So we'll take 343 plus 25 divided by 343 minus 35 times 500 hertz. What you should get is 597 hertz. Very good. Notice that makes sense because we have both the source and the observer coming toward each other. We would expect a higher frequency, and that is what we find. Now, just see if you can do this. Let's switch these directions. Let's assume that both go the other direction. What you should get then is that FO is 421 hertz. See if you get that. So, putting both the velocities in the opposite direction, see if you get an observed frequency of 421 hertz. Well, very, very good. I'm afraid that's all the time we have for lecture number 24, which is our last lecture. So that's all the time we have for Physics 1111. I hope you enjoyed it, and I hope you'll come back for Physics 1112. Thanks a lot.